All right, so let's keep a good thing going. We'll pick up right where we left off and talk about amino acids individually and specifically here. But just to give you a frame of reference, we already talked about the three-dimensional structure of amino acids in general, and we used the first portion of this lecture to talk about the things and properties that amino acids share in common across all 20. Here we'll talk about the individual side chains and their biochemical importance, different types or categories of amino acids as well, and then the last part of this lecture series will focus on the peptide bond, polypeptide chains, and small functional proteins and what they do. So amino acids themselves have a wide range of different biochemical properties, and that's largely due to their structures. Amino acids are classified into different biochemical groups based on shared chemical properties of their side chains. Again, if we continue the analogy that we started in the first part of the lecture of amino acids being the letters of the protein words, each letter brings its own unique property or characteristic to the word it's part of, and the same is true of the amino acids. They bring different properties and different chemical properties to the protein they're part of. Two of these properties are of critical importance, and we've already discussed them: polar versus nonpolar. Something that can speak that charged language with water and interact favorably with water, be encapsulated by water molecules, versus something that causes water to become more ordered, because water doesn't know what to do with it. It's nonpolar. The other subcategories are ones that we were also familiar with, starting to see the method to the madness here. The reason why I gave you the background on this material is because I knew it was coming. This is a basic versus acidic. We have side chains that can accept protons and be bases, and side chains that can donate protons and be acids. Polar side chains, not surprisingly, love water. They can engage in hydrogen bonds with water. Nonpolar side chains are excluded by water. They're clustered together because they don't speak that language of charge. As I already said, basic side chains can accept protons, and when they do so, they will take on a positive charge because that proton is positively charged. And acidic side chains can donate protons, and when that positively charged protein is lost, the side chain will revert to a negative charge. Amino acids also have shorthand names or nicknames, 3-letter codes and 1-letter codes. This is shown in this figure here from your textbook, table 3.1 from the 3rd chapter. We see that alanine has the 3-letter code ALA and the 1-letter abbreviation just A. Oftentimes in classes you'll need to memorize these. I don't have you memorize these, nor I should say will you ever have to memorize the amino acid structures. I don't see any learning value to having you do either of those. You'll be surprised though how much these 1-letter codes will become common and familiar to you as we go through the semester. And there's a method to the madness here as well. Obviously, if you use A for alanine, you can't use A for arginine as well, and you can't use A for asparagine either. So scientists have tended to go with letters that make some intuitive sense. So R is used for arginine because arginine starts with R, and asparagine gets an N because that last bit of asparagine is very N-y, asparagine. Likewise, phenylalanine gets an F because it's phenylalanine, whereas proline gets the P. And even you can have some fun with it, at least the way I remembered it. W for tryptophan, I would always tell myself that was actually twiptophan, and it was that twip sound that made me remember that the W was the single-letter code for tryptophan. So there's some ways to remember these codes if you need to in the future. So we use these single-letter codes when we're showing the sequence of amino acids. It makes it much easier to show a sequence if each amino acid is represented by a single letter rather than its full name. So the first category of amino acids we'll discuss are the nonpolar amino acids, those that are hydrophobic and can't interact with water. They are glycine, alanine, valine, leucine, isoleucine, proline, phenylalanine, tryptophan, and methionine. Here are your nonpolar amino acids. And for the most part, there's no big surprise here. Hydrogen, no charge there, so no hydrophilic behavior. This is a hydrocarbon. Always remember, hydrocarbons are nonpolar. This is a hydrocarbon. This is a hydrocarbon. This is a hydrocarbon. So no surprise that there's no polarity. And here is a hydrocarbon as well. When it gets to the rings, it's a little bit different. Methionine is considered nonpolar, even though sulfur has a little bit of polarity, but the overall side chain is considered nonpolar. Those of you who are looking close, you'll notice that this indeed is a polar bond. This is a partially positive hydrogen bound to a partially negative nitrogen. There is some polar property here. but it makes up such a small part of this huge side chain that the overall side chain is considered to be nonpolar. A subset of this group, the alanine, valine, leucine, and isoleucine subgroup, are considered aliphatic side chains. They are more linear. There's no benzene ring involved. Proline is the weirdo of the bunch when it comes to amino acids. You'll notice that proline side chain is a hydrocarbon side chain, 1, 2, 3 ethyl groups, but that last group doubles back and makes a covalent bond with the amino group itself of the amino acid. No other amino acid does this. For all of the other amino acids, the amino, carboxy, and proton groups are left alone, isolated from the side chain. Only proline makes contacts between the side chain and any of the other groups of the amino acid itself. That has structural considerations, which we'll talk about in the next lecture series. Tryptophan and phenylalanine both contain nonpolar rings, and we've already mentioned that there's a sulfur atom in methionine. Remember, these are the nonpolar amino acids. So all of these amino acids hate water, they are excluded by water, and they can engage in hydrophobic interactions. And I'm doing air quotes as I say that because these aren't really interactions, they're just the enemy of my enemy is my friend. For the polar amino acids, we break them up into two separate groups, charged and uncharged. We'll discuss the polar uncharged group first. We mentioned in our last lecture that water can interact with any molecule that has a charge. That charge can be full or partial, and these are the partially charged amino acids. There are amino acids that have full charges. We'll talk about them next. And the amino acids that we're going to name in just a moment here are those with partial charges. All of those amino acids are hydrophilic. They're all polar. Water can interact with all of them. So serine, threonine, tyrosine, cysteine, glutamine, and asparagine are our polar amino acids which contain no full charge. And we can spot these a mile away, can't we? We have a hydroxy group here, an electronegative oxygen bound to hydrogen. That's a polar bond. This is going to be partially positively charged. This will be partially negative charged. This is a polar bond. This is a partial charge bond. There's another hydroxyl group here. There's a hydroxyl group here. We talked about nitrogen being electronegative as well. And so this nitrogen is pulling on the electrons in these covalent bonds, making itself partially negatively charged and leaving these hydrogens partially positively charged. And that's true here as well. So these two nitrogens are also partial charge electronegative groups, making them hydrophilic. For cysteine, I told you that sulfur sometimes imparts some polar properties. In this case, we have no giant rings, no large side chain. It's just this single ethyl group, this hydroxycarbon. And so this sulfur group here, this SH group, thiol group, is imparting some degree of hydrophilic behavior to that side chain. So this is a good time to point out that I will not ask you, like I said, to memorize or draw the amino acid side chains in the future, nor will I ask you to memorize their names. I will, however, hold you responsible for being able to characterize an amino acid that I give you. So in other words, if I gave you threonine, its name and its structure, and I said, tell me, what group does this amino acid belong to? I expect you to be able to tell me that it is a polar, uncharged amino acid. And you can reason that out for yourself without memorizing anything. It's uncharged because you see no little positive or minus signs in the side chain. There's no full charge here. Otherwise, it would be represented by pluses or minuses in the side chain. And we know that it is polar because it has a hydroxy group. So I will expect you to be able to characterize these amino acids on your own in our first exam. Cysteine, in addition to being polar and uncharged, is a hugely important amino acid for us to consider. That thiol group is not only polar, but it also can engage in covalent bonds. When it is oxidized, which means when we strip that thiol group of its proton, the sulfur of one cysteine can make a covalent bond with a similarly oxidized sulfur of another cysteine. This results in what's called a disulfide bridge. This is a sulfur-sulfur bond across two cysteines, which then covalently holds those two amino acids together. These types of disulfide bridges allow proteins to stick to a single three-dimensional shape, which we'll talk about in Lecture 3, and it also allows different proteins to stick to each other in larger complexes. Some of you who've taken immunology or had some immunology units in other courses might recognize this structure. This is the classic structure of a typical immunoglobulin, an IgG molecule, and you will see that these subunits are being held together through, there they are, disulfide bridges. So there's a cysteine right here in this small side chain, and there's a cysteine right here. And each of those cysteines has been oxidized, and these sulfurs are now engaged in a covalent bond, holding the arms of the immunoglobulin together. And the two halves of the immunoglobulin Y are also held together by a pair of disulfide bridges, which we see here across the hinge region. It's not overdramatic to say that without cysteines and the disulfide bridges they can form, we would be dead. Life would not be possible on this planet. Asparagine and glutamine are very similar to each other. They differ only in a single methyl group. You can see that here and here. We've just popped in one additional CH3, and we've changed asparagine to glutamine. I've already mentioned it, but always keep in mind that oxygen and nitrogen are electronegative. They are pulling and tugging on the electrons in the covalent bonds that they are engaged in, making themselves partially negative, and then leaving their respective hydrogens electron poor, therefore being partially positive. On to the polar amino acids that do have full charge. Glutamic acid and aspartic acid are precursors for glutamine and asparagine, so we make these two guys here by using acidic amino acids. The other charged amino acids are the basic ones, lysine, arginine, and histidine. At neutral pH, all of these will either lose or gain their protons, respectively, and when the acid side chains lose their protons, they become negatively charged at neutral pH. When the basic side chains gain their protons, they become positively charged because they picked up a positively charged protein, also at neutral pH. And so these are our charged amino acids because as acids and bases, they have lost or gained charged ions. As I said, if I'm asked to characterize this, I don't need to go any further than this little symbol here. That little minus sign in the side chain shows me that the side chain is charged. Therefore, this is a charged and polar amino acid. Likewise, we see little baby plus signs in our basic amino acids showing us that protons have been absorbed. Histidine and lysine and arginine, again, they're basic, they're positively charged. They have accepted positively charged proteins, giving them their charge. Histidine is already an old friend of ours. It is that charge on demand side chain. It's important because it allows us to gain a positive charge or neutralize that positive charge to zero right there at the wiggle room of neutral physiological pH. Because the pKa of that side chain proton on histidine is right near 6, if we go a little bit higher than 6, towards 7, 7.5, we're going to lose that proton and neutralize that side chain to 0 net charge. And if we stick at around 6, we're going to keep that proton, keeping that histidine side chain charged. There are some other amino acids that go beyond the 20. These are uncommon amino acids that aren't typically found in proteins, but they are present, although rare. So I told you that there are 20 amino acids found in proteins, but that's not entirely true. These other amino acid derivatives can be found in proteins as well, but in very, very, very small numbers. Also, they derive from the normal 20 when they're being made. One example of this is hydroxyproline. Not surprisingly, hydroxyproline is a normal proline amino acid with a hydroxy group added to it. We can also make hydroxylysine in a similar way. And thyroxine is a concatenated tyrosine amino acid where a second aromatic ring is tacked on to the first, and that gives us thyroxine. Again, rare amino acids, but worth pointing out. So probably a more appropriate way to describe this would to be say something like only the 20 amino acids we've discussed are incorporated into an amino acid sequence during protein synthesis. Once those normal 20 amino acids have been put into place, they can be further modified and derived into other amino acids right there in situ, right there as part of the protein they were added to. Some other side notes to kind of tie up and make clear. A free independent amino acid at neutral physiological pH is referred to as a zwitterion. A zwitterion is any molecule that contains an equal number of positive and negative charges. Of course, amino acids have one positively charged amino group and one negatively charged carboxy group. So this is an ion. It has charged groups, but its net overall charge is 0 because the positive amino group is canceling out the negative carboxy group. That's a zwitterion. Yeah. So, to summarize this portion of the lecture, we talked about the different groups that we can classify amino acids into. Nonpolar, which means no interacting with water at all, completely hydrophobic. Polar, but with no full charge, so all of the hydrophilicity is due to polar bonds, partial charges. And polar charged side chains, which can interact favorably with water and are hydrophilic, but do so through full ionic charges. And this includes the acidic and basic amino acids as we discussed them. All amino acids are acids and bases because they contain carboxy and amino groups, but usually those groups are tied up in peptide bonds and can't act in that way. So that's it for this chunk of the lecture. We will resume one more time to wrap this lecture up with part C. Thanks for watching.